Here we have a work energy problem where we have a small mass at A, which is going to slide down a curved ramp that has no friction and then enter a level zone, moving over here to point C. It's connected by a spring that has a relaxed length of 1.2 meters, and it's initially moving at 5 meters per second. Now, to solve this, let's first define the concept of mechanical energy, where the total mechanical energy is the kinetic energy plus the gravitational potential energy plus any spring potential energy that we might have. And you should recall that kinetic energy is 1/2 mv squared. Gravitational energy is mgh. And spring energy is 1/2 kx squared. Now it's important to note that this x must be from the relaxed position. So x is equal to L minus x0, where x0 is the relaxed length of the spring. And we're actually told that in this problem has a relaxed length of 1.2 meters. And here h also needs to be defined by a datum. So we need to pick some location in the problem that logically makes sense to call height equal to 0. Looking at it, it's generally good practice to call the lowest point in the system h equal to 0. And that would be our datum. And from here, these terms all represent the total mechanical energy of a system. And we're told here that it has no friction, so for conservation of energy, we could say that the total energy at A is equal to the total mechanical energy at B, and would also equal to the total mechanical energy at C. So let's apply the conservation of energy to this problem and find the speed of the mass at each of the locations. So the energy here at A will be kinetic energy plus gravitational potential energy plus spring energy, which we know is 1/2 mv squared plus mgh plus 1/2 kx squared. And all these terms are given, so we have 1/2 times 2 times 5 meters per second it's initially moving at. So 5 meters per second squared plus 2, 9.8 times 1.2 meters. If we look up here, this completes this quarter of a loop, so that makes this height 1.2 meters above our datum, plus 1/2, the spring constant is 40 newtons per meter, and now we need to find x, and x is L minus x0. The length here is 1.2 plus another 1.2, so that's 2.4 minus 1.2, which would be 1.2 squared. We get 25 joules plus 23.5 joules plus 28.8 joules for a grand total of 77.32 joules. Now let's do the same thing at B. So the energy at B will be the kinetic energy plus the gravitational energy plus the spring energy. And if we look here, we've reached the ground, so we know that this is 0 now. So the energy at B will be the kinetic energy plus 1/2 kx squared, which gives us energy of B of kinetic energy plus 1/2 times 40 and x here. Now we need this length up here. And looking at this, this is a 45 degree. So this will be 1.2 square root of 2. And therefore x will be L minus x0, which will be 1.697 minus 1.2. So we get x is equal to 0.497 meters. So we can put that here, squared. So our energy at B will be the kinetic energy plus 4.94 joules. And again, everything here is in joules. Now you might wonder, why am I leaving kinetic energy like this and not plugging in 1/2 mv squared? Well, since I don't know v yet, I'd rather just leave it like that until I find that term, and then I'll solve for v independently. At location C, we have the kinetic energy plus the gravitational energy plus the spring energy. And we are on the ground, so we still have 0 here. Right? We've reached the h equal to 0 point. Interestingly enough, the spring has also relaxed, so there's no spring energy left. So at location C, we have only kinetic energy left. Let's solve for this. So it's a conservative system. Therefore, energy at A has to equal the energy at B. We're not losing any of it. At A, we have 77.3 joules, and that's the kinetic energy at B plus 4.94 joules. Therefore, the kinetic energy at B will be 77.3 minus 4.94, which is 72.4 joules. And therefore, we can now solve for the velocity at B, since the kinetic energy is 1/2 mv squared. We can multiply through by 2, divide through by m, and we'll find that the velocity will be the square root of 2 times the kinetic energy over m, which will be true at all points. So we'll get the square root of 2 times the kinetic energy divided by the mass, which happens to be 2 in this case as well. And it turns out we can find the speed of the object as the square root of the kinetic energy that it has at this point in time, which will be the square root of 72.4, which gives us 8.51 meters per second. So we see that it's gained some kinetic energy, and it's traveling now at 8.5 meters per second in this location. We also now know the amount of kinetic energy that we had at that location. It was 72.4 joules. To find location C, it's conservative again. So the energy at A equals the energy at B, and it also equals the energy at C. So we actually could just jump right to here. We didn't have to find B to get this. The energy at A is 77.32, and that has to equal the energy at C, which is all kinetic energy at C only. So therefore, the velocity at C is the square root of 77.32, which we know we can just take the square root of kinetic energy because the 2 and the 2 kilograms drop out. And we get 8.79 meters per second. So we find up here that kinetic energy is 77.32, and the velocity at C is 8.8 meters per second. And that solves part A of this. Now they also ask what would happen if we had a frictional drag force that's constant of 10 newtons acting along the system. Well, just thinking about it, it's unlikely that we'll be traveling at 8.5 meters per second here. We're going to have friction that's going to slow us down. And we won't be going 8.8 here because it'll continue to slow us down and possibly even stop us. So let's see how we would deal with this when it becomes non-conservative. For a non-conservative event, we would use the work energy theorem. Which in its strictest form is written as the sum of any work done on the system will equal to a change in kinetic energy. That's the official form of the work energy theorem. And when it's written this way, the work includes the work done by gravity, the work done by the spring, and any work done by forces F dot dr, right, our definition of work. So this work is everything other than kinetic energy, which motion is the only true pure form of energy.
Pure energy. Pure
Everything else is potential energy waiting to become motion. Now, once we understand that, we can modify this slightly, and we can take the potential energy and the spring energy and bring them to the other side, in which case we get an alternate form, which is that any work done on a system will equal to a change in the total mechanical energy of this system. And with that, we really only need to worry about tracking the work done on the system, and work, recall, integral of F dot dr. And that dot term there guarantees that these are both in the same direction. So you'll often see it as the integral of F dot dx, or the integral of F, this would be Fx, or Fy dy, and so forth. Another way to think about this is work is done along the path. If we have a curve, if the force is along the curve with us at all points, it's acting in the correct direction, in which case we can just do it as force times distance along the path. If the force were horizontal all the time, that's different. We'd have to use the dot product, and this would become the integral of F as a vector dotted with r as a vector, which would be an integral of F r cosine of theta between F and r, and so on. So in the case of variable forces, we want to integrate it. In the case of the angle changing with respect to the force and the path acting on it, we would want to integrate it as well. But in our case today, we have a constant force of 10 newtons, and it does act along the path, so we can use the simplified form for calculating the work. And the general sign notation for this is that energy into a system is positive work, and energy out is negative work. So a good example of energy out would be friction. That's a loss of energy. It's stealing energy from our system. And energy in could be something like a rocket engine that's maybe attached to it. And that will put energy into the system as force times distance as well, if they told us the force that's exerted by the rocket engine. So that's a background on the work energy theorem. And this form of it here, work is equal to the change in energy total, is very useful. So in our problem, the work done will be the change in energy, which we could write as energy final minus energy initial, any point along the path. So to go from A to B, the work done would be the energy at B minus the energy at A. So here we can calculate the work done and going from A to B as the force, which is a constant, times the distance from A to B. And the distance is the distance along this curved path right here. So the distance is 1/4 of a circumference, which will be 1/2 of pi times 1.2 meters for the radius. So the distance traveled is 1.88 meters. And therefore the work done is 10 newtons, And we could call it negative here because it's acting opposite of our motion, although we know that we're going to lose energy, so we know that it's negative. Times the distance, 1.88 meters. So the work done in going from A to B is negative 18.8 joules. That represents the loss of energy and going from A to B. Well, the energy at A was 77.32, so the energy at B will be the energy at A minus this work, which will be 77.32 minus 18.8, which is 58.5 joules. So the energy at B is 58.5 joules. And we see that it's equal to this, which is still true. It's equal to the kinetic energy at B plus 4.94 joules of spring energy. So the kinetic energy at B will be 58.5 minus 4.94, which is 53.5 joules. So the velocity now at B will be the square root of 53.5, which is 7.32 meters per second. So we find now that with this drag force, we'll be going at 7.3 meters per second here. And we won't be going at 8.8 over here any longer either. Let's take a look at that case. So in terms of bookkeeping, which is really what this sort of becomes, we know that the energy at A, 77.32 joules, that's our starting point. We just found the energy at B, the total mechanical energy, to be 58.5. Now let's find the energy at C. So the energy at C will equal the energy at B minus the work done in going from B to C. And the work done in going from B to C is the force times the distance traveled from B to C, which will be 10 newtons. And here, this one's pretty straightforward. We're only traveling from here 1.2 meters. So 1.2 meters. So the work done and going from B to C will be negative 12 newton meters, which is a joule. So therefore, we can finish this. The energy at B is 58.5 minus the work done, which is 12 joules. So we end up with 46.5 joules as the energy at C. So over here we have that. And recall at C, we have only kinetic energy left, so that's going to equal the kinetic energy. So the velocity at C will be the square root of 46.5, and we get 6.8 meters per second from that. So over here we've slowed down to 6.8 meters per second as a result of this constant 10 newtons of force acting on the system. The concept of work energy is very useful. So any work done on a system will result in a change in the total mechanical energy of this system. And it's a very nice shortcut for finding solutions to problems so that we don't have to integrate. For example, we could ask, find F, the drag force, such that it stops at C. How much force would it take for this thing to come to a perfect rest at point C? Well, that's fairly straightforward to do. Recognize that to stop at C, right here, there'd be no spring energy left, the spring is relaxed, and there'd be no gravitational potential energy left. So the energy at A, which is the starting energy for this system, would have to be used entirely by the work done by the force. So we have 77.32 joules, and that'd be force times distance. And the distance traveled would be the distance along this curve, 1.88 meters, plus the 1.2 meters along the horizontal, which that gives us a grand total of 3.08. Therefore, the force here to stop it will be 77.32 joules divided by 3.08 meters, and we'll get 25 newtons from that. So if we had a 25 Newton drag force acting on it all the way down this ramp, it would slow it down and eventually stop it at this point. We could also ask the question, if we did have this 25 newtons worth of force, could we find the velocity at B? This concept of work and energy is quite useful. We can solve fairly complicated problems with really just some careful bookkeeping. Thanks for watching.